We've been learning how to build and interpret linear regression models. Now it's important to step back to question and evaluate our work. We'll do that in this 3-part video series, starting here with part 1. One of the most famous quotes in statistics states that all models are wrong. Mainly, just like model cars, architectural models, or Star Wars Lego models, statistical models are idealistic representations of more complex realities. That said, good statistical models can still be useful or inform our understanding of the world's complexities. To know whether our model is of the useful variety, there are 3 essential questions to ask. Is the model wrong, or how wrong is the model? Is the model strong, and is the model fair? In part 1, we'll focus on the first question. Technically speaking, a model is wrong when the assumptions behind it don't hold. And it turns out that there are 4 assumptions behind the linear regression models that we've been working with. That is, our model needs to satisfy 4 properties to not be wrong. Conveniently, these spell out line, linearity, independence, normality, and equal variance. Let's start with the second assumption of independence. The assumption here is that the residuals from our model do not depend on one another. That is, they're independent. Though formal tests, which we won't get into, also exist, we can typically determine the appropriateness of this assumption by examining the context of our data collection. Consider an example. Suppose a research group wants to study typing time, Y, versus sleep hours, X. One approach that they might take is to recruit 100 people and to observe each person one time and record their X and Y outcomes. Just the first 10 data points are shown here. A second approach would be to recruit 20 people and observe each person on 5 separate occasions. In total, this would also give us 100 total observations. The first 10 data points are shown here, along with a variable that indicates the person to which the data points correspond. Now, both of these approaches produce, again, 100 separate data points. However, in modeling Y versus X, one of these data sets would lead to a violation of the independence assumption, and the other wouldn't. Pause your video to think about which one is which. Notice that in approach 1, our 100 data points are independent of one another. That is, one person's sleep hours and typing time are independent of or unrelated to another person's. In contrast, the data points produced by approach 2 are not independent. Mainly, though person 1 is independent of person 2, that is, their behavior is unrelated to one another, the observations within person 1 are not independent. That is, person 1's performance on one day is going to tell me something about or is not independent of their performance on another day. In turn, the independence or dependence among our data points can influence the independence or dependence among our model residuals. For approach 1, the 100 individual data points in the scatter plot of testing time versus sleep time are independent. Thus, their model residuals, or how far the data points fall from their regression line, are also independent. But for approach 2, our data points are not independent. In this case, neither are their model residuals. For example, the data points for person 4 are highlighted in red. Notice that this subject tends to get a lot of sleep and tends to have below average typing times. The fact that all of their data points fall below the line, or all of their residuals are negative, suggests that these residuals are not independent. They're related or tell us something about one another. Consider another assumption, linearity. The assumption here is that our model equation accurately describes the relationship between Y and X. That is, at any X value, the Y outcomes are balanced around our model trend. Here, beta 0 plus beta 1X. Equivalently, residuals are balanced around 0. To check this assumption, we can examine some plots and consider context. That is, it's important to ask ourselves if the assumed relationship between Y and X makes sense. For example, the scatter plot of typing test time versus sleep time confirms that the relationship is indeed linear. thus is accurately represented by the linear regression model Y equals beta 0 plus beta 1x. However, the relationship of temperature in Minnesota versus day of year is not linear, thus is not accurately represented by the simple linear regression model shown here. We can gather as much from the scatter plot. The model line doesn't capture the quadratic pattern in the data points, but it's also important to use our critical thinking skills and context. The assumed linear relationship between temperature and day of year simply doesn't make contextual sense. In the Northern Hemisphere and a four-season location like Minnesota, it doesn't get warmer and warmer throughout the year, as suggested by the model line. Rather, as represented by the data points, the year starts off cold, and then gets warmer and warmer into the summer months, and then tends to get colder and colder as we get into fall and winter. Next, consider the normality assumption. The assumption here is that at any x value, y outcomes are normally distributed around the model line or trend, beta 0 plus beta 1x. Equivalently, at any x value, residuals are normally distributed around 0. Though there exist formal QQ plots and tests for normality, we can gain insight into this assumption by examining our scatter plot. Consider our plot of typing test time versus sleep time. This red box here zooms in on observations with roughly 7 hours of sleep, x. In this region, the test outcomes y are roughly normally distributed around the regression line. And what I mean by this is that the y values are clustered around the line, and we observe fewer and fewer observations falling further from the line. Essentially, the cloud of points fades as we get further and further from the line. And importantly, this is roughly true for all x, not just sleep times around 7, no matter what sleep outcomes we zoom in on. Next, consider the assumption of equal variance. The assumption here is that the variance of y outcomes around the model line beta 0 plus beta 1x is roughly the same at any x values. Equivalently, the variance of residuals around 0 is roughly the same at any x value. Again, plots provide insight into whether this assumption is met. In our scatter plot of testing time versus sleep time, let's compare two regions, observations with sleep times x of roughly 6 hours and roughly 8 hours. Notice that the variability or spread of the sleep outcomes y is roughly similar in these two regions. Importantly, this is roughly true across the entire range of x values. That is, there's roughly equal variance or scatter across the entire model range. Now, in evaluating our model assumptions, there's a catch to relying on context and plots of our data alone. We'll soon be studying more complicated models that have 2 or more predictors. Thus, they live in higher dimensions, like the model shown here, where we have 4 predictors. Unfortunately, it's tough for humans to wrap our minds really beyond 3 dimensions, meaning we typically won't be able to visualize such high-dimensional models, thus we won't be able to check our linearity, normality, and equal variance assumptions by plotting these models. Instead, we'll utilize a visualization tool called a residual plot. For example, consider a plot of the raw data for our test time versus sleep time analysis. The highlighted data point here corresponds to a person that slept 7.1 hours and had a test time of 55.3 minutes. Yet, based on their sleep, we would have predicted a test time of only 52.9 minutes. Thus, the residual for this data point, or the prediction error here, is 2.4 minutes, calculated by the observed y outcome of 55.3 minus the prediction of 52.9. Now, whereas the axes of the plot here correspond to the y and x outcomes of the raw data points, a residual plot plots the residuals on the y-axis versus the fitted values or model predictions on the x-axis. The dot circled in the residual plot here corresponds to the same raw data point circled at left. It has a fitted or predicted value of 52.9 minutes and a residual of 2.4 minutes. In general, every dot above 0 represents a similar data point in which the observed test time was above the model prediction, hence has a positive residual. In contrast, each dot below the 0 horizontal line represents a data point in which the observed test time was lower than predicted, hence has a negative residual. So what does the residual plot alone tell us about our linearity, normality, and equal variance assumptions? First, notice that the horizontal line represents residuals of 0, and the residuals here are balanced above and below this 0 line across the entire range of the plot. Equivalently, this implies that the data points are balanced above and below our model. Hence, our model accurately describes the shape of the relationship. That is, the linearity assumption holds. Next, notice that the residuals are normally distributed or clustered around 0 across the entire range. We observe fewer and fewer residuals far above or below 0. Finally, the variability in or the span of the residuals is roughly equal across the entire range. Stepping back from this specific example, in general, a good residual plot is one that looks like a random scatter of points. That is, there are no obvious or interesting patterns in the residual plot. Determining what looks random or not random simply takes practice. With that, let's consider some bad residual plots. First, consider our inappropriate linear model of Minnesota daily temperatures versus day of the year. The residual plot corresponding to the simple linear regression model is shown here. It too has some interesting patterns, and patterns in residual plots, again, are bad. Specifically in this example, the residuals are not balanced above and below 0 across the entire range of the plot. Rather, we observe clusters below 0, then above 0, then below 0. This imbalance confirms that our model at left violates the linearity assumption. Consider another example. Here, our linear regression model cuts down the middle of two separate but linear clusters of points. Correspondingly, the residual plot has an interesting pattern, and again, patterns in residual plots are bad. First, though goofy, the residuals are balanced above and below across the entire range. Thus, though this isn't a good model, as in it doesn't actually capture our two clusters of data points, it doesn't exactly violate the linearity assumption. However, it does certainly violate the assumption of normality. Mainly, the residuals here are not normally distributed around 0. Rather, they fall in clusters above and below 0. Consider a final example: the raw data and model shown at left, and the corresponding residual plot shown at right. Again, the residual plot definitely has a pattern which is bad, but in what way is it bad? Well, the residuals are balanced above and below 0 across the entire range, thus the linearity assumption is okay. In other words, the linear model at left here does accurately capture the linear trend between y and x. This model also satisfies the normality assumption. The residuals are roughly normally distributed around 0 across the entire range. That is, we see fewer and fewer residuals at each fitted value as we get further from 0. However, the model does not meet the equal variance assumption. In the left plot, we observe more and more uncertainty or variability in the y outcomes as x increases. Correspondingly, in the residual plot at right, we observe more and more variability in the residuals as the fitted values or predictions increase. Technically speaking, we have heteroscedastic, not homoscedastic errors. In conclusion, we've learned about the 4 assumptions behind our simple linear regression models and how to check these assumptions. Importantly, if these assumptions are not met, our model is wrong. And if our model is wrong, it may produce misleading interpretations, predictions, and inference about the actual population relationship that we're studying. In that regard, some assumptions are more important than others. I think it's safe to say that linearity is the most important assumption. If that doesn't hold, meaning our model misrepresents the general relationship between y and x, then everything that we use that model for will also be wrong. I also think it's safe to say that normality is the least important assumption. Non-normal residuals will only produce misleading results in extreme situations. For example, when there's extreme non-normality, or when we have access to only a small sample size. What we didn't yet address is what to do if any of our model assumptions are violated. In brief, if our model violates the linearity assumption, we need to rethink our model structure. We may need to transform our variables, for example, from a linear to a quadratic scale, or include other variables in our model, and so on. We'll explore these ideas later in the semester. If independence is violated, we can seek out different modeling techniques that are designed for correlated data. We will not get into such techniques this semester, but examples include multi-level, time series, and spatial models. Finally, if our model violates the normality or equal variance assumptions, we might be able to transform our variables. And when that doesn't work, we might seek out different modeling techniques. For example, though we won't get into them this semester, options exist beyond the normal linear regression models.